little statement first, just to remind everybody here that the interpretation of data is only as good as our understanding of processes. And the tools that have been developed in the context of BGH have been extremely interesting for people interested in making some progress on our understanding of processes. So I would like just to share some thought today, in particular about anomalous topography. We have heard over the past couple of days some comments about anomalous uplift and subsidence that seems to exist in every single margin and basins. And over the past few years, with a number of students, including Omer Bodur and Luc Mondi, we have been doing some work, to try to nail or to try to explain some of those anomalous topography. So this is the work of Omer Bodur. He was a PhD student in BGH. And what we were interested to understand was the role that the shear stress acting at the base of a plate could play in triggering episode of uplift or subsidence. We had trouble actually to convince our reviewer that the numerical modeling we were doing using Underworld did document indeed something very important. And over the past year, what we did was, to put the numerical modeling aside and to try to have another approach. And that's what Omer has done with the guidance of Greg Hasman. So what we've done here, what Omer has done, was to solve the stream function to extract information about the topography and the tempo of that topography in relation to the relaxation of stress acting at the base of a plate. And that shear stress is the one which is related to either the motion of a plate above a static mantle or the one related to the flow of the asthenosphere underneath the plate. It turns out that the topography is not a function of the viscosity structure of the plate, but it's only a function of the amplitude of the shear stress, which is S0 here. And it turns out that the timing or the tempo of that topography is a function of the viscosity, as well as, of course, the density contrast between the plate. If we plot the topography as a function of wavelength, that's the graph on the left, and if we plot the timing of the topography as a function of the wavelength of the flow, and that's the graph on the right, it turns out that shear stresses can drive dynamic topography up to 100 meters, and this can occur in a few hundred of thousand years. So that's a first interesting message. 100 meters doesn't seem much, but if we are dealing with a margin, which is typically close to sea level, you can explain some interesting phase of flooding and emergence. The second message I want to propose here is the fact that sediment supply can trigger depth and stress inversion. And that's the work of Luc Mondi, and Guillaume Duclos was also involved in that work. So those are rift model, quite similar to the one that Rebecca presented yesterday. So they are isostatic scale model, high resolution. We implement sedimentation on those model. And what we're interested to understand is how that sedimentation impact on the stress field. So on the left, we have a rift model at 6 and 10 million years. In brown, we see the crust, upper crust, lower crust. The lower crust is in dark brown. And the pale green underneath is the lithosphere, and in white is the asthenosphere. That blob here is partial melting. And in red, what we have is the fault or shear zones, is the accumulated plastic strain. And the stratigraphy is color-coded here for time. What we observe is that initially, during the first few million years of that rifting system, the entire lithosphere is pretty much under extensional stress regime, except for some little blue part here at the base of the crust, or even in some basins. But as you form that asthenospheric dome, very quickly the mantle underneath the crust turn into a compressive stress regime. However, what we also observe is that right in the sediment package, we can observe some negative stress, so compressive stress. They are localized, and they have an amplitude that can exceed 20 megapascal. So here it seems that we have an explanation for those anomalous phase of stress inversion that are relatively localized in time and space. Perhaps more interesting is what happened when we turn off the sedimentary supply. When we turn off the sedimentary supply, what we have is a phase of isostatic rebound. And that's what we show here on that graph. What we represent here is the average basement depth across that entire rift here. And we show that when we stop the supply, and this circle here shows the timing at which we stop the supply. We stop the supply at 20% extension. For the gray curve here in red, we turn off the sediment supply at 35. And you see this phase of uplift straight away. As soon as you switch off the sedimentary supply, you have this phase of uplift, and that's a phase of uplift can be, of several kilometers in amplitude. And in fact, the meaning of that is that what that cessation of sedimentation does is to introduce a dynamic imbalance in the system. And we observe here through this experiment a competition between the loading of the surface through the accumulation of sediment, and this compete with the imperative that the asthenosphere has to reach its neutral buoyant point, which stands about 3,000 meters below sea level. So as long as we pile up sediment, this loading impede the exhumation of the asthenosphere. However, when we stop sedimentation, you have a dynamic imbalance, and then very quickly the asthenosphere rises, and you have this depth inversion. And we are wondering, in fact, if many of the breakup and conformity that have been mapped in mini basing and continental margin could be explained in part by this process. The last thought is about dynamic topography. And here I will invite you to read the paper for Peter Molnar in 2015 published in Tectonics. We explained that when you observe the initiation of the delamination of the base of the lithosphere, and if you look at the flow field, what you expect is not a subsidence but an uplift. And that was, I find, interesting. And for this, we ran some experiment. And here I show you the snapshot. And that experiment, so let me quickly describe what we try to do here, is we impose a temperature anomaly here, somewhere underneath the lithosphere. So the continental lithosphere is there. We impose a temperature anomaly. This led to a density anomaly, and that anomaly sinks. We, of course, the magnitude of that anomaly simulates some sort of slab. And what we are keen to look at is the flow field that is the result of that sinking process. So this is the situation 20 million years after initiation. You see that, interestingly enough, we trigger a secondary radial instability. But what is more interesting is if we look at the streamline, you realize that through time there is a number of eddies that develop. The first one being the label A here, and that it's just a convective cell, that bring things down and pull in the lithosphere. And with this, you observe this topography, this dynamic topography here in pink. So initially, within the first million years, you observe a dynamic subsidence of a few hundred meters. And as that little anomaly sinks further down, we observe a second eddy. And this one is quite interesting because the flow here is upward. And when you look at your profile here, what we observe is you see some interesting uplift here on both sides here of that anomaly. And in fact, when you start to, that thermal boundary base of the lithosphere start to be dragged down, we have in fact a third eddy again triggering subsidence, and this explains here that little trough in between these two shoulders. So we find that quite fascinating. So it's a work in progress, but it looks like the flow field in the case of a sinking anomaly is a bit more complicated than we thought, and perhaps we can explain some of the anomalies that have been observed in the Northwest Shelf, for instance, through this process here. And I stop there. And I will also thanks everyone who has contributed to BGS success